Alright, class, this is our video, our second video for this week, and we're mainly going to be dealing with a couple of different things. Uh, First, we're going to be talking about a little bit more on talking about sampling distributions and the central limits theorem. This is actually more material out of chapter 6 in your book, kind of near the end of that chapter, and it's more conceptual stuff that's not 100% necessary, but that you need to know this to be able to perform the calculations in this class and to be able to interpret the statistics, but it's important for that kind of foundation on how inferential statistics works. So we're going to cover that, and then we're also going to cover confidence intervals, which is another thing that we'll be calculating. So we'll have first some more conceptual stuff here, and then some more stuff with actual calculations. Hooray, more calculations, right? I don't know, you guys might actually make the calculations better than the conceptual stuff. But let's start off talking about, this is going to segue us into our discussion of sampling distributions, but let's just review a little bit on samples and populations. As you recall, samples are basically a subset of a population. But one thing we can say about samples is that they generally provide an incomplete picture of a population, because again, you're not asking every single person in a population or every single thing in a population, you're not observing it, you're just taking a small part of that and trying to infer from that to the population. So there's always the chance that your sample isn't really a good representation of your entire population. I mean, for example, if you're interested in voting behavior, obviously we wouldn't got a sample of 5th graders. That wouldn't be a good sample for that particular population. In fact, it probably wouldn't even come from that population. But to give you a more concrete example of this, this is one reason we always have to be careful when we're drawing conclusions from samples, because there's always the chance they're not accurate. And then, depending if you guys take a research methods class, there's obviously a lot of things you can do to make your sample more likely to represent your population. I mean, obviously the biggest thing we talked about was have an actual random sample. But there's still some problems you need to be aware of. And to give you an example of kind of a past example of a sample of a population going wrong when it came to predictions, we can use a presidential election example here. Usually when presidential elections come up, there's all kinds of agencies that basically do polls to try to figure out, they go out and ask people in the general public who you're going to vote for, and then they try to figure out who's going to win the presidential election. We still have that. It's pretty common today. I mean, the Gallup poll was probably still one of the most common with that. But kind of an example of sampling going wrong, we can look at the 1936 presidential election, which was between Franklin Delano Roosevelt and Alf Landon. And this is particularly a poll that was done by a popular magazine at that time called Literary Digest. And this was actually a huge undertaking. They actually sampled about 10 million people, which was essentially their readership. So everyone that was subscribed to Literary Digest got basically something in the mail saying, okay, who are you going to vote for? But it didn't just sample from its own readership. There was also basically people that were registered to own automobiles were sent this as well, and then people that had a listed telephone number. So that's kind of who they polled in this. Well, what ended up happening, they essentially predicted that Alf Landon would win the presidential election. They actually predicted that he would win by a pretty large margin. Well, obviously, since you guys probably have never heard of Alf Landon before, FDR is actually who ended up winning the election, and this is a pretty big hit to Literary Digest's prestige and actually really hurt them because they basically were, after they did their poll, they're saying Alf Landon's going to win. Well, when that didn't happen, they had to start looking at, okay, well, what went wrong here? And it really came down to, okay, who were they sampling? And the people they were sampling didn't represent a whole of the United States population. So they had some major sampling error there, and that they essentially weren't using sampling means or sampling frames to actually that represented the entire population. And you can kind of see this 1936, that was kind of during the Great Depression, and so quite a lot of people in this country were poor at that time. However, almost everyone they sampled in this some 10 million sample that they had, which is a ridiculously large sample, you don't even need something nearly that large to predict something like a presidential election. But the people they sampled were essentially the more well-to-do people in the country. people that could still afford a magazine subscription, people that had automobiles, and people that had phones. Again, having automobiles and phones in that time period was kind of rare. If you didn't have the money, obviously, that wasn't something you were going to go for. So there's huge segments of the population they didn't include. So that's just one thing. I mean, the first thing when it comes to sampling, you need to actually make sure that your sampling frame actually represents the sample that you're doing. But then if that happens and you do a random sample, you can generally be fairly sure that your sample is at least somewhat representative, but there's always the potential that you just randomly selected a bad batch. But anyway, what we're kind of getting to here is that any sample has what's called sampling error. You want to remember this term. Basically, this means the amount of error or discrepancy between a sample statistic and a population parameter. And again, if you do a bad job drawing your sample and you don't do it randomly, then you're probably going to have a lot of sampling error. One of the things that you learn in your research methods classes is how to really reduce that amount of sampling error. But even if you do everything right, there's still going to be a small amount of sampling error, at least some amount. So going back to that example. I mean, another example of this today would be if you're doing a study and you only used people who have the internet. And again, if say you were looking at certain segments of the population, you'd be leaving people out. So there's always flaws with different ways that you collect your data. But okay. But again, if you do things correctly, then you don't have as big of a problem. And that's one reason that we do, again, a random sample. All the statistics that we talk about in this class rely on you having drawn a random sample because that's what has the lowest amount of sampling error out of the different sampling techniques that are out there. Now this leads me to my discussion of sampling distributions. Now let's do some distinguishing here between different types of distributions. Remember that a frequency distribution would be a distribution where every value in your sample is basically represented on that distribution. Now, a sampling distribution is actually when you would take multiple samples and you take each test statistic from those multiple samples and plot those onto a graph. Then you would have your sampling distribution. Now the sampling distribution, it's another one of these theoretical distributions. You would never actually do this because with a sampling distribution, it's kind of this assumption that you take basically an infinite number of samples, and if you took the mean or whatever test statistic you're looking at and plotted those all out on a graph, that would be your sampling distribution. So let's say we had one mean, let's say we're looking at rolling dice here. And we do trials of 10 and basically get the mean on a six-sided dice on those trials of 10. And so that would represent, if we were to basically take that trial of 10 and plot out each one of those, we'd have a frequency distribution. But in this case, if we then calculated the mean from each sample, so in this case, each time we rolled the 10 dice, and we calculated the mean of each of those, and plotted those on here, we would begin to get what's called a sampling distribution. So if we rolled a dice 10 times and calculated the mean of that and got a mean of 3, we would plot that here. Maybe next time we got a mean of 5, a mean of 1, and so on and so on. You start plotting it out. All you really need to remember for now is that a sampling distribution, again, is this theoretical distribution where you would take an infinite number of samples of something you're testing and plot those out on a graph. Again, you would never do that, but we basically know a few things that if we did do this, what would happen. And we essentially know that if you did do this, that if you had a population that was normally distributed on a particular value, we know that if your sampling distribution's mean, let's say this is the mean here, would actually, if you took that infinite number of samples, would represent the true population's mean. And it would essentially form a normal curve. So that's a pretty important aspect of that there. Now again, this sampling distribution would be made by essentially taking, let's say we're doing a sample of people's heights within the United States. And we kept taking random samples of 100 people and calculating their heights. Well, each one of those random samples might end up in different places on this and eventually begin to stack up in different places. And again, if we took an infinite number of those, it would essentially take on this shape. Which was essentially our normal distribution. And we also know that in that case, if we did take that infinite number of samples, that our mean of that sampling distribution would equal the mean of the population. So if our mean height was 6 foot in the population, the sampling distribution, even though each sample probably wouldn't be showing a mean of 6, the actual mean of the sampling distribution of sample means, I know that's a mouthful, because each of these represents a sample mean, and then the sampling distribution is a sampling distribution of sampling means. Well, its mean would represent the actual population and be the same as the population's mean. So, in the sampling distribution of infinite sample means, the values of the means will vary from sample to sample, but they will cluster about the true population mean. There's another way to say it, kind of taking that directly from the book there. And another thing that we know is that within this sampling distribution of sampling means, again, the sampling distribution's mean would represent the same as the population, and the standard deviation of this distribution of sample means would be equal to standard deviation of the population over the square root of n, which basically just represents standard error, which we've already talked about a few times, sometimes abbreviated as FSE. Now this generally works on any sample size if you have a normally distributed population. However, a lot of times, again, a lot of stuff isn't normally distributed in the population, for example, like murder rates. But what's interesting about that is there's something called the central limits theorem. And I just have some, if you guys go up and look at the actual PowerPoint I posted, you'll have some of this posted on there with some of the stuff I just said. So, central limits theorem, again, coming back to that, let me actually kind of pull up a applet online to demonstrate this. But before we look at that, let's what's the central limits theorem say? It basically states that if an infinite number of random samples of size n are drawn from any population with a standard mean mu and a standard deviation sigma, then as the sample size n becomes larger, the sampling distribution of sample means will approach normality, which a mean of u and a standard deviation of sigma divided by the square root of n, even if the population distribution is not normally distributed. So it's basically a theorem that shows that as long as your sample size is increasing, then your mean of your sampling distribution will still equal the mean of your population, even if the population mean isn't normally distributed. And so what that really means is that we can use this central limits theorem to essentially apply probability theory to almost any type of testing, and we'll see this a little bit later when we go over our confidence intervals. But let's go and look at that applet I was talking about. Now what this applet shows is the number of cases and number of samples. So the number of samples is set at 1,000, so it's not even the infinite number of cases that we would see with a true idea, since this is a theoretical distribution, this distribution of sample means. But what this represents, we can see that as we change this scale here, which represents sample size, we can compare this line, which is our, in this case, our population distribution, to our sampling distribution. You can see the sampling distribution doesn't match the population distribution, but where the mean would be would still be the same location. And as you increase sample size, that range narrows, so you actually get a more accurate estimate of your sampling means to your representation of your population mean. Alright, that's probably a little bit confusing. All you need to remember for this class is that we can look at that page 234 in your book in that little box. We can assume that the mean of a sampling distribution is equal to the population mean. And this is all based on stuff that people, mathematicians and statisticians have figured out for many years, and we can just rely on this being true. But kind of three things here. We know that we can assume that the mean of the sampling distribution is equal to the population mean. We can also assume that the standard deviation of the sampling distribution is equal to basically standard deviation of the population divided by the square root of n, your sample size. And we can assume the sampling distribution is normally distributed even if the population from which that sample was drawn is not. This really boils down to the fact that we can use probability theory in a lot of different ways when it comes to our inferential statistics and applying samples to the population by using that sampling. Alright, I'll give you guys a little study guide for the test because you're only going to need to know a little bit of that. But what you're going to need definitely to know this next part, which is about confidence intervals. And what these basically are, a confidence interval is essentially an estimate of how, it's basically a range of variables that you can know with a certain degree based on what we just talked about captures your true population value. So, as I put here, sometimes we want to see how likely a parameter in our sample represents the population. So we're generally talking about means here as our basic examples. And we know with our knowledge of sampling distributions that because if we have a large enough sample, we can basically say that the sampling distribution is normally distributed, and we know what the mean and standard deviation or standard error of that sampling distribution is. We can basically calculate how likely our own sample represents the true population. So what this really does, the confidence interval gives you a range of values that is to some degree or another likely to represent the true population parameter. And it's a plus minus figure. To give you guys an example here to maybe make this make sense, you often see these confidence intervals in the real world when it comes to political polls. Now you might see something like 40% of Americans plus or minus 3% believe that the economy is getting worse. A lot of times in polls you would see that stated. This plus or minus basically represents our confidence interval here. And basically we can calculate intervals with various levels of probability of being true. And we usually set those at 95 or 99%. So for example, if we use a 95% confidence interval here, or whoever calculated this, they could say with 95% certainty, 40% of Americans believe in the economy getting worse, plus or minus 3%. So they're generally saying that the true population mean would fall somewhere between 37 and 45%. And there's a 95% confidence that that is true. Now, let's move on to your formula for this. Your formula for calculating confidence intervals around a sample mean basically depends on your sample size. Just like when we were looking at our z-test and one sample t-test before, your formula is different on that. And this really comes down to when you can rely on the central limits theorem. And basically, rule of thumb, if you have a sample, your book says 100, but we're going to go with 30. If you have a sample that's 30 or below, you would use this formula, which uses a z distribution. And if you have above 30, or sorry, if you have 30 or above, you would use the z distribution. If you have 30 or below, you would use this over here. And they're basically exactly the same, just you're using a different distribution to get your critical value. So to find z, you would get the z table and look at that. And basically we'd just be plugging stuff into this formula in each case. And z on here would basically be, we would plug in a critical value based on whatever level of confidence we wanted. And we would use our z table, which we already saw in the other video how to do that. But if we were below 30 sample, we would use this over here. Only difference is this value here would be found on the t table using, again, we'd have to know the degrees of freedom and once again kind of what level of confidence we want to have. Alright, as usual, this will probably make more sense after an example. Let's say we were testing, we had a sample of hackers that were arrested. Let's say there was 40 hackers that were arrested, and we find that these hackers have a fairly decent IQ, it's 112. And we want to kind of figure out, okay, how likely is it that the general population of hackers in the rest of the United States that haven't been arrested, how likely is it that this population actually represents this sample represents the entire population? So let's say we got the following information. We have 40 hackers that were arrested. We get an IQ of each. The sample mean of this sample is 112 with a standard deviation of 9. We want to determine how likely our sample represents the population. So sample hackers versus population of hackers. And let's say we want to use a 95% confidence interval. Okay, first thing I can ask here, after what we just covered a second ago, what formula would we use in this case? Well, because we have a sample of over 40, we would use this formula with our z table value here. Alright, so we know we want to use this formula. So, let's get our z value here, which we know that we're setting a 95% confidence interval. So to kind of get the flip side here, that means we want a 0.05, which again would represent an alpha level for a 95% confidence interval. And with most confidence intervals, you're going to be doing basically 2-tell because you want that confidence interval to be stretched out in both directions of your normal curve. So what we would end up getting here with a 0.250, which would represent that we get 1.96 once again. So z equals 1.96 for the 95% confidence interval. We already know x bar, plugging that in, equals 112.8. Standard deviation equals 9. And our n equals 40. So let's plug all this in and do our calculations here. So we would know that 1.96 times 9 over square root of 40. So let's get that first. What's our square root of 40 here? Alright, so square root of 40, what do we get there? We would get 6.31. Have to do a little bit of rounding to get that. 6.31. And, okay, 9 divided by 6.31. We would basically get 1.43, which this represents our standard error. So, last thing we need to do is times 1.43 by our z-score we already got, which is 1.96. Times 1.43, and for that we would get, let's see, 2.8. So now, okay, we know Z is 1.96. After calculating everything there, we get a 2.8. So now what do we do? Well, we would just take our mean and subtract 2.8 from it, and then also add 2.8 to it, and that would give us basically a range of 110 through 115.6. And so that would be our confidence interval here, 110 through 115.6. And we could essentially say that based on our sampling, the idea of sampling distributions, what we know about sampling distributions, we can be 95% certain that our true population mean is somewhere within this 110 through 115.6. However, there's always the chance that we're kind of on that 5% of distributions that basically don't very accurately represent the true population mean. Alright, well, if we had a smaller sample, let's do another example here. Well, if we had a smaller sample, let's say we had 20 individuals arrested for hacking, and we get the following, same values. Actually, correction there, I changed it where we had a nice rounded sample mean here of 112. But nevertheless, let's say that we had this smaller sample. Well, in this case, because we have the smaller sample below 30, we would use the t here. Otherwise, the formula is exactly the same. So the big difference is that we have to find that t value by looking at our t table, which we saw in our last video, and it used for a different purpose. But let's pull that up again. As you can see, here's our t table. All right, we got a sample of 20. And since this is technically two-tailed, we go over and find two-tailed, 0.05. 2.086 is what our value would be for that. So 2.086, or sorry, should actually be 2. Oh, sorry, I actually made a mistake there. Let's go back, because when you're looking at this table, remember you have to take degrees of freedom into account. So we should actually be looking at 19 here, and then going over to our 0.05 two-tails, and we get 2.093. So our answer here would be 2.093. Remember, don't forget to take degrees of freedom into account there, like I did. So now we can just plug everything into our formula once again. Okay, the first thing we want to do is get our square root here, which would basically give us which would be 4.46, I believe. Divide that, or n divided by that. Which gives us a standard error of 2.02. We then times that value by our 2.093 here, which would eventually give a result of 4.23. So plus or minus 4.23. And then our next step, as I said, is just taking that 4.23, adding it to our mean of 112, and also subtracting it to give us that range. And if we add that together, add and subtract it, it would give us a range of 107.77 through 116.23. So our interpretation here, we could say that we are 95% certain that the true population mean falls somewhere between 107.77 and 116.23. Now, just a few closing remarks here. The reason we're able to figure all this out is, again, based on that knowledge of the sampling distribution, and that we know that the sampling distribution is essentially a normal distribution, and we also know what the standard deviations of that distribution would be, which would basically be this here. So really that essentially represents a standard deviation on that normal distribution. And so based on that, we're able to essentially make these calculations and estimate with a certain degree of certainty how likely the variable that we have falls, or sorry, the mean that we have and the confidence interval that we calculate captures the true population value. Now, my concern for this next test is you guys can calculate and interpret confidence intervals in this manner, but you also want to read the chapter in the book pretty carefully to kind of get the background on how this works and how we have this information. Other than that, I think that should be enough for this week. You guys want to start studying for your test. I will have a little bit of a study guide up this time to kind of direct you on what to study. And then next week we'll be moving into the more traditional, or some of the type of statistical techniques that you'll basically be using a lot more often if you're actually going out and collecting research. So, hope you guys have a fantastic week. As usual, if you have any questions, feel free to contact me. And that is it.